Don't bump my thing. Don't bump that. Don't bump that. Because I have that set to be like on the screen. All right, so quietly get those. What is your first question from the homework?
A, B, C,
Hold up, I have
D,
one
E,
earlier
F,
than that.
Anybody go lower than 74?
72.
62.
63.
Can anyone go lower than 62?
I mean like 30, 34 and 36. The right train. What, 34?
Yeah, I just think
Yeah, I had no idea.
time and they got it.
34, 36?
I don't understand.
All right. So we're going to start with 34. 34, I've got the boxes. So arrange in order from highest to lowest. Let's do the easiest one first. 34B. Same. Does that make sense? Why? Why is it all the same for 34B? All the same temperature, all the same kinetic energy. All the same temperature. If they're the same temperature, they're the same kinetic energy. 34A is pressure, right? 34A is pressure. Pressure depends on what two things? Force over area, right? Yes? Force is also just your number of what? Collisions or particles, yes? So for A, my lowest pressure is going to be II2. Why? Least amount of particles in the same area. But that's going to be equal to, because you can have equal to 6. Why? Same amount of particles, right? Same amount of particles in the same area, which is going to be equal to what? That's going to be equal to 1. Why? Wait, no, that's going to be less than 1. Whoa. All right? That's going to be less than 1. All right? Why does one have a higher pressure? Smaller, right? Less than 1, which is going to be equal to 5, which is also going to be equal to 7. It's going to be equal to 7, which is also going to be equal to 6. I'm sorry, 4. Also going to be equal to 4. Which is going to be less than 3, which is going to be equal to 7. So that's your pressure. Did I do 7 twice?
I think the first one was supposed to be 8.
Yeah, this one was supposed to be 8. That's my bad. There we go. That makes more sense. So that was pressure. B is the same. C is density. We know that density is mass divided by volume, right? So I'm going to look at mass and volume. So for C, my least density is going to be what? 2. That's going to be 2, which is going to be less than what? 1, which is going to be equal to 1 is going to be equal to 4. Why? Why is 1 and 4 equal? Twice the mass, but also twice the area. So the density does not change. So 1 is equal to 4, which is going to be equal to what else? 6, right? Which is going to be less than 3, which is going to be equal to 5, which is going to be equal to 8, which is going to be less than 7. I think you could maybe see something like this on a multiple choice, but not like writing out. All right? There'll be something particle-wise on multiple choice, but I'm not going to make you do something like this all written out on the test. Test is mostly math. D is root mean square velocity, which accounts for both temperature and the mass of the particles. Is the temperature changing for any of these? The temperature's the same, right? So which one's going to move slower? The heavy one or the light one? The heavy one, which is what? Argon. So that means V equals VI equals VII equals VIII, which is less than 1, which is equals 2, which equals 3, which equals 4. So that one was just based on the mass of the particles.
See, how do you know 3 is higher than?
How do I know that 3 is higher than 6? So 3 has how many particles in it?
8.
8 particles, right? In half the volume. 6 only has 4 particles and double the volume. That was 34. Next one. 36. So, which are true, which are false? Is this mostly you just want to see if you got them right, true or false? Yeah. Okay. 36A, at constant temperature, the lighter the gas molecules, the faster the average velocity of the gas molecules. What'd you say for A? True. A is true. What about B? So B, at constant temperature, the heavier the gas molecules, the larger. False. The heavier the gas molecules, the larger the average kinetic energy of the gas molecules. That's false. What about C? A real gas behaves most ideally when the container volume is relatively large and the gas molecules are moving relatively quickly. 36C. That's true. That's super gassy, right?
I said false because it has no volume.
But the more, that's what gases want to do, right? The more a gas can be like a gas, the more ideal it is, right? So that is a very gassy thing. So the more gassy it is, the more true. Ideal gases want to have no volume and they want to be moving all over the place. So that's true. Letter D, as temperature increases, the effect of interparticle interactions on gas behavior is increased.
True.
False.
I agree.
What interparticle interactions?
The dude who fixed it said it doesn't matter in the textbook when he made the correction.
What dude?
When it was like fixing it, they were like, you have to correct it because of all these things, and he was like, it actually doesn't have that big of an effect.
What are you talking about? A dude that you read about in the textbook,
Yeah.
or? Oh,
Dude in the
okay.
textbook.
So interparticle interactions on gas behavior. That's basically talking. That's just it's just saying like forces collisions. That doesn't matter. That's false.
It doesn't matter when
When I'm trying to.
Right. So on this one for D, as temperature increases, the effect of interparticle interactions on gas behavior is increased.
Ideal gases don't have that.
It's about the effect,
When
so it doesn't.
a higher temperature, more kinetic energy,
Right? So only ideal gases.
But this is saying the effect of interparticle interactions. All right? It's because it says the effect. Yes. We got to keep moving. I don't want to spend a ton of time on this. Yes, Danny.
Ideal gases don't have interactions, right? They don't have forces.
They don't really want to have interactions. Correct. And then letter E, at a constant V and T, gas molecules are added into a container. The number of collisions per unit increases, resulting in a higher pressure. True. That's true. F, the kinetic molecular theory predicts that pressure is inversely proportional to temperature at a constant volume. False. False. That was 36. Next one.
62, right?
62? All right. Here we go with 62. Oh, I didn't work that one last period. That's great. I love that you guys are asking questions that the other period did not ask, because that means you can watch the other period.
Go over to last period, the other period.
I didn't do 62. I did not do 62. So, 62, a bicycle tire, right?
Yes.
Is filled with air to a pressure of 75 psi at a temperature of 19 degrees Celsius. Riding the bike on asphalt on a hot day increases the temperature to 58 degrees Celsius. The volume of the tire increases by 4%. What's the new pressure in the bicycle tire? Actually, I think we might have done this one, but it might have been out of order. I think we just maybe talked about this one. So on 62, I have P1 is 75 psi. T1. So we decided, just for the sake of being consistent, we're going to put everything into Kelvin temperature from now on. All right? Let's just put it all into Kelvin temperature. So for the test tomorrow, convert it to Kelvin. Okay? So my T1, 19 plus 273 is 292. So my T1 is 292 Kelvin. And my V1, they don't give me. Let's assume 1 liter.
Oh, okay.
P2. My pressure is what I'm trying to figure out, right? So that's X. T2, it went up to 58. So 58 plus 273, what is that? 331. 331 Kelvin. So what am I going to assume my V2 is? 1.04 liters. Combined gas law. You're going to have to assume something, right?
No, that-
You'll have
I
to
didn't know-
assume
I
something.
didn't know what to assume it was.
You could assume it's 100. You could assume it's 1,000. It doesn't matter. As long as it's a 4% increase for your volume. As long as it's a 4% increase for your volume. So the answer you should have got, you should have ended up with 82 psi. So after you do your ideal gas law, you should have ended up with 82 psi. 81.7, that's fine.
So we didn't.
I would just
actually
check your math.
convert to atmospheres or anything.
No, you shouldn't have to change it to atmospheres.
Do you technically have to convert to Kelvin? Like, again, we will always change the right thing.
You can actually you can sometimes get a different answer. It's kind of weird because you're in two different scales. Right. So really it is two different scales. And if we're talking about ideal gases, we really should be just doing Kelvin.
If you have a negative, you didn't convert, then yeah.
You did?
That's what I did.
So you would do
Yeah, I did. I also did.
75 times 292. I'm just have to write this out. So I have 75 psi times 292 Kelvin.
Not times that.
Oh, shoot, you're right. 75 psi times 1.0 liter over 292 Kelvin is equal to X times 1.04 liters over 331 Kelvin. So I'm going to do 331 times 75 equals, divided by 292 equals, divided by 1.04. I got 81.7. Remember, cross multiply. So this times this divided by whatever's left.
If we do 75,
You should end up with 81.7 or 82 psi.
Yeah, I agree.
Just algebra.
75, I agree.
75?
Yeah.
How did you guys like those extra explanations, by the way?
I still haven't read it.
Ah, okay. Well, I can't.
I mean, I haven't read the last two.
Okay.
It's longer, so maybe.
Okay. 75. On 75, we've got a balloon.
I give up.
Right? Yes? What are we filling this balloon with? Hydrogen. Yes? So well, the first thing to figure out is our number of moles of hydrogen. So NH2. That's going to equal PV over RT. Summing what I have. I have 1.0 ATMs times, I'm going to put a little bit of stoic in my thing because I can. So I have 4,800 meters cubed times 1 meter cubed is 100 centimeters cubed times 1,000 centimeters cubed are in 1 liter. You agree that's all accurate? Yes. Remember, you're going to have to cube that 100. To cube that 100. Over 0.08206 liters times atmospheres over moles times Kelvin times 273 Kelvin, because I said it was at 0, right? Solve for N. So my N of H2, I ended up getting 2.1 times 10 to the fifth moles of H2. Here's where it gets weird. All right? How much H2 did I actually get in the balloon? What percent actually went in?
80.
Only 80%. So I need to take 0.80, right, times the total volume, that's what I have to figure out, yes, of the balloon. That's going to equal the 2.1 times 10 to the fifth moles of H2 that I just put in. This is the tricky part, because we're trying to figure out the total volume of the balloon. Once you do that, I don't even know what you get. So I need to do 2.1 times 10 to the fifth divided by 0.80. Does that sound right?
No, just times 0.80.
Solving
Oh,
the total
yeah.
one.
Yeah, 2.1 E5 divided by 0.80 should get a bigger number, right? So this gives me 2.6 times 10 to the fifth. So I would have needed 2.6 times 10 to the fifth moles of H2 to fill the whole thing. Agreed? Because I only got 80% in there? Yes? Okay. So I'm going to take this and I'm going to convert that to grams of iron. So I'm going to take my moles and I'm going to do my 2.6 times 10 to the fifth moles of H2, and I'm going to do some fun stoic. 1 mole of H2 from the balanced equation is to 1 mole of Fe, and 1 mole of Fe is still 55.85 grams of Fe. So that gave me 9.5 times 10 to the 6 grams of iron. That's part 1. Part 2. I now need to find grams of H2SO4. Yes? So I'm going to start with the same number. So I'm going to start with my 2.6 times 10 to the fifth moles of H2 times 1 mole of H2 is to 1 mole of H2SO4. Great. I'm very excited for you. That was exciting to me too. 1 mole of H2SO4 is 98.09 grams of H2SO4. But what percent H2SO4 am I getting? Only 98. So I'm only getting 98 grams of H2SO4 out of every 100 grams of H2SO4. So that's my 98%. That's where I did it. Multiply that through, and I don't know what I had, 2.6 E5 times 98.09 times 100 equals, divided by 98, 75. So that gave me 2.6 times 10 to the 1, 2, 3, 4, 5, 6, 7 grams of H2SO4. What number was that? 75? Let's see what the book got. Yes.
What's that K right there? K over 170?
What K?
It's 1 liter.
1 liter.
That's 1 liter. That's 1 liter. 75, the book got 2.6 times 10 to the 7th. So I got the same thing. This was the only tricky thing on 75. Figuring out the total volume of the balloon.
What is that by the rate between 0 and 8206?
Liters times atmospheres over moles times Kelvin. Just the constant. Next one.
I had 78.
No,
If I do 78.
Okay, yeah, I do want to do 78. I do want to do 78. On 78, did anybody do Pivnert 3 times? Didn't have to do that. So on 78, I have a pressure of C3H8, which is 0.500 megapascals. Agreed? That was given?
Yeah.
I have a pressure of NH3, which was 0.800 megapascals. And they also gave me a pressure of O2, which was 1.500 megapascals. Here's what I did. I assumed megapascals, right? We know that due to Avogadro's law, pressure and what are directly related? Pressure and particles, right? Yes? Pressure and particles directly related. Well, could I also say that pressure and mass are directly related? Based off of that?
Yeah.
Yes. So could I just say, for every 0.500 megapascals, and I turn my coefficients from the balanced equation, I have 2 megapascals of C3H8 for every 2 megapascals. I want to do C3H3N. I took it to one of my products. 2 divided by 2 is what? So that would give me 0.500 megapascals of C3H8. And H3 also was a coefficient of 2. So for every 2 megapascals of NH3, I had 2 megapascals of C3H3N. That should be C3H3N. So 2 divided by 2 is 1. So that gives me 0.800 megapascals of C3H3N.
This is really devastating.
I know, this is devastating for the amount of work you did. The last one, I have coefficient of 3 for my O2. So for every 3 megapascals of O2, I have 2 megapascals of C3H3N. That ends up giving me 1.00 megapascals of C3H3N. Which one is the least?
C3H8.
Which means that is my limiting reactant. Which means, which one do I need to use? This one, right? So I'm going to take my 0.5. So I'm going to say I've got 0.500 megapascals. That's the one I have to use. Agreed? See?
Yeah.
I got to convert this though. Into what? ATM. So 0.500 times 10 to the 6 pascals, right? Because 10 to the 6 would be my megapascals. And I know that there's 1.013 times 10 to the 5th pascals in 1 ATM. I gave you that conversion in the notes. I'll give you any conversions you need in the test tomorrow. Also, they're up there. A lot of them
You
are.
need to memorize R.
Nope, it's up there on the yellow card. I'll also put it on the test if you can't see it. I'll put it up on the board for you. And this gives me 4.94 ATM. Now we're down to PivNert. So now we're ready for our PivNert. N equals PV over RT. So N equals 4.94 ATM times 150 liters, which was given, divided by my constant 0.08206 liters atmospheres mole Kelvin, times the temperature 298 Kelvin. That gave me 30.3 moles of C3H6. Am I done?
No.
No. I want to know grams of what? C3H3N, right? So now I have one more line of stoich to do. So I'm going to take my 30.3 moles of C3H6 stoich step. For every 1 mole of C3H6, I have 1 mole of C3H3N, and 1 mole of C3H3N is 53.06 grams of C3H3N. I ended up getting 1.61 times 10 to the 3rd grams of C3H3N for my final answer. That was 78. Or you could have done PivNert 3 times. And you should have got the same thing. Should have got the same thing. Next one.
Can we do 80?
No, it makes sense.
What? You want 80? Yes? Sure. Number 80. I have urea. Right? I'm going to find mine. On 80, I have urea. So, this is made of what? NH3 and CO2. Yes? So, they gave me ammonia at 223 and 90, flows into a reactor at a rate of 500 liters per minute. Carbon dioxide, different thing, flows at 600 per minute. Here is how I did number 80. On number 80, let me flip my page. On number 80, I did Pivner for both things. So on 80, I started out with N equals PV over RT. So for the first one, I had 90 ATM. I didn't do the second period either, so this is good. Times 500 liters per minute. I left a minute in there. You'll see why in a second. Over my constant, 0.08206 times 496 Kelvin. After I do that, that's going to give me what for units? It's going to give me moles per minute, right? Because minutes will not cancel out. So I should have put my L to ATM, moles, Kelvin, all that stuff. So that gave me 1.1 times 10 to the third moles of NH3 per minute for the first one. Then I did the second one. N equals PV over RT. So this one was 45 ATM times 600 liters per minute over 0.08206 liters atmospheres over moles times Kelvin times 496 Kelvin. These were at the same temperature. This one gave me 6.6 times 10 to the second mole of CO2 per minute. Because that was CO2. Agreed? So then what did I do? So I have two different rates. And on 80, they're asking me to figure out the grams per minute of urea, right? So, which one of those is smaller?
6.6.
I said NH3 was the limit.
NH3 needed.
NH, what's that?
NH3 is the limit.
Why is NH3 the limiting reactant?
You do more ratio.
Because the other one isn't acidic, the other one.
So for number 80, look at the balanced equation. For every one CO2, I need double the amount of NH3. Do I have it? No. So this is my limiting reactant, even though it's in a rate. So now I'm going to use that to do the stoic. So the 1.1 times 10 to the third moles of NH3 for every 1 minute. I know for every 2 moles of NH3, I have 1 mole of urea, and 1 mole of urea is 60.06 grams of urea. Moles cancel out, leaving me grams per minute of urea. So I got 3.3 times 10 to the fourth grams per minute of urea. My final answer. Is that the next one we want? 81. Number 81. I did not do this one last period, so that's great. You guys are asking ones that I did not do, so I like that. Number 81. Is 81 CH4NH3O2? Is that the right one? Yes. Okay. Hydrogen cyanide is prepared commercially by the reaction of methane, ammonia, and oxygen. Number 1, write a chemical reaction for the equation. Did you guys get the chemical reaction? Yeah. So 81, I had,
No, 10.
what?
Oh, sorry.
CH4 plus NH3, we'll get to it, plus O2 yields HCN plus H2O. Balance this bad boy. Gonna have to have a 2 here, a 2 here, a 3 here, a 2 and a 6. Does that look right?
Thank God this is
Okay. So on 81, they gave me 20 liters of each, right? Yes? Okay. Liters is a volume. Okay, so here's what I did. You guys aren't going to like this. I had 20.0 liters of CH4. For every 2 liters of CH4, I have how many liters of HCN? 2 liters of HCN. How many liters of HCN does that give me? 20.0 liters of HCN. I had 20.0 liters of NH3. For every 2 liters of NH3, I had 2 liters of HCN. How many liters of HCN did that give me? 20.0 liters of HCN. I also had 20.0 liters of O2. For every 3 liters of O2, here's my stoic step, I have 2 liters of HCN. That gives me 13.3 liters of HCN. Done. Limited reactant. That's your answer. 81. Cool?
Can we do 91? I know it's like, should be probably easy.
It's okay. It's all good. We're not going to be... Okay, 91. I'm glad we're doing this one. So I got this picture on 91, right? On 91, this is essentially going to be P1V1 equals P2V2. So my first setup, I have 2.00 liters in the first bulb, right?
Yeah.
Times 475 torr.
Yes.
That's equal to, the second one is,
Oh, later.
it says assume the final volume is what? 3, because I opened the thing, right? Once I open that thing, it's in everywhere. Agreed? So my second one is 3 liters times P2. So my P2 I got here is 317 torr of H2. So that's part 1. Then, what's the total pressure in torr? So now I have to kind of do this again for the other one. So I'm going to do my P1V1 equals P2V2 again. On the other side, I started out with 1.00 liters of nitrogen, right? Times 0.200 ATM. That's equal to P2 times 3.00 liters. So this P2 ends up being 0.0667 ATM. I got to convert one to the other, or does it tell me what to make it into? In torr. So this ATM, I know that for every 1 ATM, I have 760 torr. So 760 times 0.0667, I got 50.6 torr of N2. We probably should have said, yeah, that was H2. And we know P total would equal PN2 plus PH2. Add them together. So that's going to equal 50.6 torr plus 317 torr. And I got 386 torr for my total pressure. So you need to do the P1V1 on both sides. On both sides.
568.
568 where?
Oh, the answer.
368. Yeah, that should be. 368. You said 568.
All right.
Yeah, 368. That was 91. 101? You okay with that? Yes? Okay. 101. I also did not do this one last period. It's good. Can I turn my page? Okay, so this is 101. Sodium chlorate. All right, 101. Sodium chloride decomposes. Did you write a balanced equation? NaClO3 decomposes to produce sodium chloride, which is NaCl, plus oxygen gas, O2. Balance it. 2, 2, 3. Boom, we're balanced. On 101, they are saying the oxygen collected over water occupied 57.2 milliliters at a temperature of 22 Celsius and a pressure of 734 torr. Calculate the mass percent of NaClO3 in the original sample. At 22 degrees Celsius, the vapor pressure of water is 19.8 torr. So on this one, we know that P total is going to equal PO2 plus what? pH2O. Agreed? Yes? Did they give me the total? They did. 734 torr. Is equal to, they did not give me oxygen, but they did give me water, right? Yes?
Yeah.
Which was 19.8 torr. I can now figure out my pressure of O2 by subtraction. So PO2 ends up being 714 torr. Convert that to ATM. There's 760 torr in 1 ATM, which equals 0.939 ATM of O2. Pivnert. N equals PV over RT. So N equals 0.939 ATM times 0.0572 liters, that was given, over 0.08206 liters atmospheres, mole Kelvin, times 295 Kelvin. That gave me 2.22 times 10 to the negative third moles of O2. But they're not asking for moles of O2, they're asking for a percent, right? So now I've got to do stoich. So I'm going to take my 2.22 times 10 to the negative third moles of O2 times stoich step. For every 3 moles of O2, I have 2 moles of NaClO3, and 1 mole of NaClO3 is 106.49 grams of NaClO3. So I got 0.158 grams of NaClO3. Percent equals part over total times 100. My part is the 0.158 grams. They gave me the total, right? 0.8765 grams times 100, and I got 18.0% for my answer. I think these are kind of fun because there's not a lot of new math here. It's a lot of what we've been doing. It's just figuring out how to get to the math we've been doing, right? So you have to figure out what gas law or Pivnert do you have to do to get to the math that you know how to do. Next one.
Can you keep that up for a second?
Yeah.
We're going back to 74.
Yeah. I don't know.
We're good with the higher ones, the molar mass ones. You guys are good with the square root of the molar mass stuff? Yes?
For like 120, 122.
120? I got 63.7. Is that how you did 120? So I had rate 1 over rate 2 as molar mass 1 over molar mass 2, 24 over 40.78, 16.04. That was my 120. That's just algebra then. You got to square. You have to do some. You probably forgot to square somewhere. That was 120. What? I did do that with my other class. Yes. I will post both. I did 120. I did 107. I did 145. What number are you asking for, Reese?
74.
I did not do 74, so I'll do that one. I'll do that one. 74. Going backwards here. Concentrated H2O2. What volume of pure O2 would be collected at 27 to 46? Would be generated by the decomposition of blah, 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 all that stuff. So on this one, I'm starting out with 50% H2O2 by mass, right? So they started out me with how much? 125 grams, right? Divided by 2 for the 50%. So I'm starting out with 62.5 grams of H2O2. So that's my stoic. 62.5 grams of H2O2. Molar mass, 34.02 grams of H2O2. And 1 mole of H2O2. There is 2 moles of H2O2 for every 1 mole of O2. And that was from the balanced equation. So that gave me 0.919 moles of O2. V equals nRT over P. And after you work that through, you end up getting 23.0 liters of O2. That was 74.
107.
107. I can do it. On 107. Oh, snap. All right, no, I do want to do this, but I'm gonna show you the first part. All right? So the first part, I did this last period, so watch this on the video. First part, I did grams to moles to N2. So I got my moles of N2. Are you guys cool with that? Then I piv-nerded it to get my partial pressure of nitrogen. That's the partial pressure. Then I figured out I've got 3 moles of N2 to 4 moles of H2O to 2 moles of CO2. So there's 9 total moles of gas. Agreed? This is the partial pressure of N2, which is only 1/3 of the 9 moles. Which means I have to do what to this number? Times 3. I worked that whole thing out second period. But that's the basis of that problem for 107. So we had to figure out that that was the partial pressure, which was 1/3 of the total. N2 was 1/3 of the total. I did 107, 120, I had 145 also, second period. So you can go back and watch that. Between the 2 classes, we did almost all of them.
Did you do 140 yet?
140?
I always see the answer for your getting
140 was what? A glass container? I will find that. 140. Make sure you do the review sheet. Do the review. Do the review. This test should be easier than the last test.
No, I got like 3 tests tomorrow.
You have 3 tests tomorrow? Sheesh. 140, the answer should be 7 milliliters.
Wait, what?
140, the answer should be 7 milliliters. I haven't worked that one out yet. So 140, you have to figure out your moles of HE removed. So piv-nert to get your moles, right? In the original class, you had this many moles of HE. So you have to subtract. So you take your moles removed, subtract
They didn't give us
to get your partial. What?
They didn't give us original moles.
On 140? Yes, they did. On 140,
That was what
the original pressure. Sorry, the gas in the first container showed 1.71.
Yeah.
Right?
Yeah.
So you're going to take your 1.71, the original,
Oh, okay.
right?
Yeah.
Minus the 1.96, which is, they gave you that too. So they gave you the 1.96. So they gave you those, you subtract them to get the 0.250.
Can I picture that?
Yeah, you can. Once you have the 0.250, you have your pressure, you have your moles, and you just pivot it. So that's 140. So like I said, it's not hard math. You just have to figure out, yeah. And the good thing is there's like 2 or 3 ways to do it. On this test, most of the problems have 2 or 3 ways you can do it right.